This is the lecture on section 7.2 on trigonometric integrals. We've already seen several examples about how to integrate trig functions, for instance using a good U substitution or something like that. What we're going to see now is a fairly systematic treatment of integrating combinations of trig functions that can't be done in a really convenient way, say using integration by parts. And this section contains a lot of different variations. I can't necessarily touch on all of them with examples, so we're going to do a reasonable relative sample of these things, and I'll make pointers to the text for lots of other examples. So the first type of integral that we want to look at, the most basic ones, are integrals of the form antiderivative of sine to the m of x times cosine to the n of x dx. So I'm integrating a product of some power of sine functions and some power of cosine functions. And there are three essential cases in here, and I'll do one example and then I'll show how things work out in general. So here's an example. We want to compute the antiderivative of sine cubed theta times cosine to the fourth theta d theta. Right, so I have a product of, that's a sine cubed theta, not a sine 3 theta or sine. Let's make that absolutely clear. So I have a power of sine functions, a power of cosine functions, and that's the thing that I'm trying to integrate, their product. And I would definitely not try integration by parts here, because if you take one of those as your u and one of those as your dv, that dv choice is not going to be easy to integrate. Okay, so we have to try a different technique here. And the basic strategy for these is to use trig identities in order to simplify the integral to a point where you can use a u substitution. So we're going to take trig identities that lead us to a good u substitution. So for instance, in this particular case, we'll use the Pythagorean identity, sine squared theta plus cosine squared theta equals 1. In this case, we'll use that as sine squared theta equals 1 minus cosine squared theta. So we rewrite this integral as, we're going to split that sine cubed theta up into a sine theta times sine squared theta, and then we've got that cosine to the fourth theta and our d theta. Now the reason that this helps is the following, is using that Pythagorean identity that I have, I can rewrite this entire bit here in terms of cosine thetas. Right? The fact that I have an even power of sine there tells me that I can use that Pythagorean identity to get rid of all the sines, except for this one that I kept out front, which goes with my d theta. So if I have u equals cosine theta, then this bit in red is essentially my d theta, off by a sine. Right? So let's make that absolutely clear. That's the big picture. Here's how it gets implemented. So we're going to rewrite this as, I'm going to move this sine theta over with the d theta. So, yes, we'll rewrite this as sine squared theta cosine to the fourth theta times sine theta d theta. And now let's give that sine theta d theta a minus sign. So I need a minus sign out front here. And then I can rewrite that sine squared as 1 minus cosine squared theta times cosine to the fourth theta times minus sine theta d theta. And now I do my u substitution minus the antiderivative of 1 minus u squared times u to the fourth times du. And I can simplify. That's just a polynomial now. So bring that minus sign inside because it's convenient. The antiderivative of u squared minus 1 times u to the fourth du. Multiply that expression out. Antiderivative of u to the sixth minus u to the fourth du. And I can take that antiderivative over here as 1/7 u to the seventh minus 1/5 u to the fifth plus c, and then I put my expression for u back in, which is u is cosine, so 1/7 cosine to the seventh theta minus 1/5 cosine to the fifth theta, all plus c. Okay. Notice that what was key for this strategy to work is the fact that that exponent on the sign exponent 3 here is odd. That allowed me to pull apart the sine into a sine squared and a sine so that I had that sine theta d theta for my du. So in summary, with your power of sine and power of cosine integral, you're going to have three possible flavors. If you have the antiderivative of sine to the odd power of x times cosine to anything dx, you're going to, so this is the first option in part A, you're going to rewrite that as sine to the even power x cosine to any power times sine x dx. And you can rewrite this bit all in terms of cosine, and then this bit also in terms of cosine, and then this leftover bit you will use for your du minus du in this case when u equals cosine x. If instead the power on cosine is odd, so sine to the mx, don't care what m is, cosine to the odd power of x dx, you're going to do a similar thing, but you're going to factor out a single power of cosine. So we have antiderivative sine to the mx cosine to the even power x cos x dx. You'll rewrite all of this in terms of sine x. That'll be your u value, and then over here this will be your du with no need for worrying about the sign. So these two cases deal with the situation where one of your exponents is odd. The only remaining case is when both of the exponents are even, and in that situation you need to use the squared identities for the trig functions. So sine squared x can be written as 1/2 1 minus cos 2x. Cosine squared x can be written as 1/2 1 plus cosine 2x. And then you're going to simplify and apply one of the previous techniques. Okay? So in the interest of time, I'll just point out that examples of these two cases can be found in the text in examples 1 and 2 on page 471. There are two nice examples of this form. Those are examples 3 and 4 in the section. And for more description of the general strategy on page 473, you can see the red box for the general strategy for these types of integrals, that is, with powers of sine and powers of cosine. The next flavor of integral that you'll have to deal with in this section, call this part B, is when you're integrating powers of tangent and powers of secant. And the idea is the same. You've got two possible substitutions that you're going to try. You'll have u equals tan x or u equals secant x, which will work sometimes depending on what the powers on tangent and secant look like. And to see the general strategy, you should look at the red box on page 474, and then you should also look at examples 5 through 8. So there are 4 examples of integrals of this form that are computed in the text. Lots of good examples. What I want to do instead of showing you one of those is to show you something that the book doesn't show you, which is the similar strategy for integrating powers of cotangent and cosecant. Now what's true is that the strategy for these is similar to the strategy for part B, the tangents and secants. But let me show you how that manifests in some examples, or in an example. And for the example, we're going to need to recall a couple of formulas. So first of all, we need to remember that the derivative of the cotangent function is negative of the cosecant squared function. And similarly for the derivative of the cosecant function, that's minus the cotangent times cosecant function. The other thing that will be useful here is the Pythagorean identity that relates cotangent and cosecant. I don't have that one memorized, but I'll show you how I recover it in practice. And that's by taking the Pythagorean identity for sine and cosine, and now I have sines and cosines. What I want is cotangents and cosecants, and the way I get that is to remember that cotangent is the same thing as cosine over sine. So what I need to do in order to get the identity that I want is to multiply the left and right hand side here by 1 over sine squared x. So I use the denominator that I have in this expression here. And that simplifies to sine squared x over sine squared x plus cosine squared x over cosine squared x equals 1 over sine squared x. So 1 plus, sorry, that denominator there should not be cosine squared, but sine squared. So I have a cotangent squared x, and that's equal to cosecant squared x. So these three formulas are the ones that are going to be really helpful for the problems that are in this track C with cotangents and cosecants. So here's an example for us to consider. I want us to integrate take the antiderivative of cosecant to the fourth x times cotangent to the sixth x dx, and using those formulas. Now, because remember that we have that the derivative of the cotangent function has cosecant squareds in it, and using the idea that we had before, the fact that the number of the power on cosecant here is even suggests that I should use u equals cotangent x here, because I can collect together two powers of the cosecant. Of course, there shouldn't be a dx there yet. Two powers of the cosecant for my du, and the remaining powers of cosecant I can get rid of using the Pythagorean identity. So we'll rewrite this as the antiderivative of cosecant squared x cotangent 6x cosecant squared x dx. And then let's see here. Cosecant squared, what was our Pythagorean identity that we had? 1 plus cotangent squared x equals cosecant squared x. So I have the antiderivative of 1 plus cotangent squared x times cotangent to the sixth x times, let's have a minus cosecant squared x dx with a new minus sign outside the antiderivative. And now here I have everything in terms of u's, and over here I have exactly my du. So I can rewrite this as negative antiderivative of 1 plus u squared times u to the sixth times du. This one looks exactly like one that we did in a previous example. Let me not go through all the steps of showing you how to multiply that out and take the antiderivative. We end up with minus 1/7 cotangent to the seventh x minus 1/9 cotangent to the ninth x plus c. Okay. The next form that we have, form D, and this is the last one that's written explicitly in the notes, is things of the form antiderivative of sine of nx times sine of mx dx, antiderivative of cosine nx cosine mx dx, or antiderivative of sine mx cosine nx dx. And the strategy for these uses some formulas that you're going to have to memorize. This one's got trig identities that we're going to have to commit to memory. And the general strategy for these, we have a red box on page 476. And one of the examples, example 9, shows how that strategy works in general. Instead of showing you an example like that, which you can read in the book, what I want to do is I want to show you an example of one of the problems that they don't give you a nice example of in the book. And that's the following. So let's look at an example like this. Cosine squared x times sine 2x dx. Right, so this doesn't fit into one of the previous forms that we had, because the last type had sine mx and cosine mx, but it didn't have powers. And so we haven't seen yet a strategy for dealing with mixture problems like this. And there are all sorts of variations on this. And the basic strategy is for you to just hammer on it with trig identities until you get it into a form that you can deal with. Okay. And so the useful trig identity for this one, I picked this one in particular because there's a trig identity that comes up over and over again that we haven't seen yet, and that's the double angle identity for sine. Sine 2x is 2 sine x cosine x. And if you put that in to this particular integral, we have the antiderivative of cosine squared x times 2 sine x cosine x dx. And for this one, you see I have a single power of sine and then multiple powers of cosine, so I can now use u equals cosine x du equals minus sine x dx as a substitution. So we'll end up with, I bring that 2 outside the integral plus a minus sign because of my minus sine x dx, antiderivative of, we'll just rewrite this as cosine cubed x times minus sine x dx, and make my substitution minus 2 antiderivative of u cubed du, so minus 2 times 1/4 u to the 4th plus c, so we have minus 1/2 cosine to the 4th x plus c. General strategy for problems like this, if you don't see an obvious trig identity to use and it's not in one of the preceding forms, you should try to convert everything into sines and cosines. And the last thing that I want to point out is a couple of examples in the book give us some nice formulas that we're going to be using later, and that is the formula for the antiderivative of tan x dx. And that's one we computed using the quotient rule and a u substitution in section 5.5. That's the ln absolute value of secant x plus c. One that we didn't compute in a previous section, but it is explained on page 475, is the integral formula antiderivative of secant x dx, which is ln absolute value secant x plus tangent x, of course, plus c. Okay, so those are formulas that will definitely come up later that you're going to want to add to your fantastic list of formulas that you've been memorizing all semester. All right, so this is the end of the lecture, section 7.2 on trigonometric integrals.